Hello, and welcome to this webinar on leveraging a VI-grade desktop simulator into your system engineering process. I am Scott Bergeon, Technical Lead for North America at VI-grade. Today, we will be talking about desktop simulators and the role they play in the engineering process. We'll start with some simulator-related industry trends, discuss the impact of simulators on the development process. Then we will look briefly at the VI-grade simulator lineup, followed by a deeper look at the desktop simulator. We'll wrap up with some case examples and conclusions. So let's start with some industry trends related to simulators. First, and this is much broader than just simulators, there's an increasing complexity in product design and lineup, especially when it comes to powertrains. More electric vehicles and hybrids are being introduced. This hasn't diminished the need for developing internal combustion engine vehicles, though, as they will continue to be dominant in the market for the coming decade and beyond. With this complexity, there is continued pressure to develop programs faster. This includes the desire to reduce the number of prototypes, which has a direct impact on simulator use as alternatives to physical prototypes are increased into the development cycle. To support simulator use, there's a need for high-fidelity real-time models. Models that are more complex, more accurate, at higher frequencies, and across more use cases, while needing to be kept up with real-time computing environments that enable simulator use. And finally, a related trend is the way that simulators can act as a process integration hub, which, more than physical prototypes do, tighten the relationship between the CAE departments modeling the vehicle design intent and the drivers and evaluators that do the subjective assessment. This means that drivers need to be closer to the CAE process to understand what they are in fact evaluating, and the CAE teams need to be closer to the drivers as their models are directly used in the simulators. Now, let's take a look at the development process and the role that simulators play in shortening the development process. The traditional System V development process starts with a concept design and target setting at the full vehicle level, usually supported by physical benchmark testing. Targets get cascaded to the system and down to components. Designs get created and assessed using classic CAE and other design tools. Then combined back up the right side of the System V, the classic approach focuses on hardware testing at the component and then system level before progressing to sign off using a prototype. Some of the subsystem evaluations also get done with physical prototypes or mule vehicles. This process tended to separate the role of CAE from the evaluators that worked with physical prototypes. Commonly, the evaluators are focused on answering the what of design, as in, what is the performance relative to the targets? Interaction with the CAE gets relegated to the why or how, as in, why is the design not meeting a target? Or how will we adjust the design to balance competing targets? But not necessarily establishing the what. With a shift from physical prototype and mule testing to a simulator-centric process, the role of the CAE team and the test drivers is brought closer together. This allows for more effective target setting by bringing the targets, as represented by the real-time model driven on the simulator, into a direct subjective evaluation during the target setting phase. To the extent that mule vehicles were used in the past to establish targets, they can be done with design intent models on the simulator. It also allows for an earlier and more effective sharing between OEMs and suppliers, where both entities can assess design intent with a driver-in-the-loop process. This can be done at the system level, starting with target equivalent models, proceeding with software-in-the-loop evaluations, and finally with hardware-in-the-loop validation if needed. The development cycle can be shortened because the component and system level sign-off can be done with simulators in a consistent way with how targets were set, and without waiting for expensive, in cost and time, mule or prototype builds for testing. So in the development cycle, the use of simulators can be used in several phases. First, for vehicle level target setting, this includes the ability to assess benchmark vehicles, which can be captured on the simulator through modeling that is based on measurements on the very type of data that the system targets are based on. It includes design intent models derived from initial concept designs and can include simulator models that have been adjusted to align with program-specific targets. And this allows both objective and subjective evaluations of the targets in a way consistent with how target trade-offs are done. Second, since the vehicle level targets assessments on the simulator are based on models built up of the various system and subsystems, the cascade of targets and design evaluations at the subsystem level can be straightforward. Not only are there consistent subsystem measurements in the models to use for targets, but they can be assessed directly on simulators in a consistent way where the rest of the vehicle model is available. And third, the sign-off phase. Here, high-performance design intent subsystem models can be brought to the simulator for verification testing. For subsystems like controllers and ECUs, or other systems that have high nonlinearities that are difficult to capture in models, a hardware-in-the-loop approach for simulator use can be done. This might be a steering system, brake system, or driveline as examples. Rather than placing the hardware into a mule or full vehicle prototype, however, they can be directly connected on a simulator. Not only does this shorten the time used in building the prototype, but it also allows the subsystem to be assessed in a design intent model directly in the same manner as the targets were set. In other words, the rest of the vehicle during that evaluation is design intent as opposed to a mule that may or may not be true. So there's a vision for a system development process that is simulator-centric, that has promised to bring significant value to the development cycle. There are several challenges to this vision, however. One is in the models. Simulator-ready models require a high level of investment and quality. It's common for models that are used for offline analysis to be brought into a simulator, and issues are identified that were missed or even intentionally overlooked in the offline environment. An example is vehicle dynamics models and atoms, or other multi-body dynamics tools, may be run offline without realistic traction control or ABS controllers included. Without those controllers, the real-time version of the models may be undrivable. Though higher fidelity models are needed and will take an investment, it's worth pointing out that this investment highlights the very aspects of the model that present themselves on the simulator that are critical and would be present themselves in a prototype-based process as well. Another challenge is the simulators themselves. The evaluation done on simulators works best when done by experts who have experience using simulators and are familiar with what can and what can't be effectively evaluated, both from the capability of the simulator itself and from the limitations of any specific model being evaluated. This isn't, in my view, any different than the limitation that arise from mule and prototype builds being evaluated, which themselves are not the same as driving production vehicles. Another issue, and again prototypes suffer from the same restriction, is that simulators, especially large simulators, are usually resource limited. Our experience working with customers is that when simulators are truly integrated into the design process, they quickly get saturated with program use. Maximizing the efficiency of time in the simulator becomes important. That usually means minimizing the amount of non-production time on the larger simulators through use of smaller simulators for model preparation and checkout. And another challenge is working across the supply chain between OEMs and suppliers to have an effective simulation-centric process. Not all suppliers have a mature simulator process in place to supply models to the OEMs or to effectively utilize supplied models. Suppliers may struggle to work with multiple OEMs that each have a different modeling environment, different software, and different needs. And, of course, managing model sharing in an environment where design intent needs to be shared for the simulator models to be effective, but intellectual property needs to be preserved. This can be a challenge. To that regard, VI Grade has developed a family of simulators and simulation solutions, starting with offline simulations. Here, the goal is to develop desktop simulations that can represent full vehicle attribute objective assessments through integrated CAE tools. This includes real-time modeling for vehicle dynamics, traffic and sensor modeling for ADAS applications, and NVH desktop modeling. There are all CAE approaches based on model environments that are directly accessible to simulators, used on the desktop as CAE tools first. The first level of true simulator is the desktop simulator, which is what our topic for today is. These simulators use those same models but include a driver-in-the-loop capability. The goal here is to bring in that richness of driver interaction with the CAE models in a package that is accessible to engineering teams. It's also done on a computing platform identical to our larger simulators. As the focus on this talk, we will come back to talk more about this solution. The next level of simulator is a compact simulator that brings in the ability to get direct, subjective assessment of vehicle dynamic response. Here the focus is on the human response and bring dynamic cues to all the human touch points and sensor modes in an approachable package and cost. This includes rich graphics, accurate steering feel, brake and accelerator pedal feel, and cues for the vehicle dynamics. For NVH, this means including vibration response across and on top of a rich sound response that is available even at the desktop level. The next level of simulator in terms of richness of response is a static simulator. This brings in the possibility of a full cockpit, even a full vehicle, for a richer visual environment that is particularly useful for ADAS and HMI scenarios that might even include non-expert drivers. And at the top of the spectrum is a family of dynamic simulators, the VI grade driver in motion or DIM simulator family that are designed to provide a large range of travel for longitudinal, lateral, and yaw dynamic response. So let's talk just a little more about these solutions. For offline simulations, VI Grade's Car RealTime product is our best-in-class solution. With Car RealTime, we have a faster than real-time solver with a rich modeling environment that supports either a KNC style suspension data set or a hard point with bushing rates, including nonlinear bushing suspension design. It comes with a VI driver that is a best-in-class robotic driver solution, providing driver inputs to match path and speed control, including all the way to the limit handling capability. Car RealTime fully supports software-in-the-loop modeling through either a Simulink or a direct MATLAB accessible solution. Car RealTime allows you to deactivate subsystems and replace or augment them with Simulink models. The solution can be run native in MATLAB, useful for control design engineers. It also supports a compiled auxiliary subsystem approach for bringing in models for running in a Car RealTime native environment. Both solutions support an investment mode for efficient design of experiment studies and optimization. In addition to Car RealTime, we also provide a traffic sensor modeling solution in VI WorldSim. VI WorldSim allows for definition of traffic scenarios for ADAS testing. WorldSim is built on the Unreal Graphic Engine for state-of-the-art graphics, and as such is one of two graphics solutions that VI Grade includes with most of our simulators. In addition to defining traffic scenarios, WorldSim provides a direct simulation of sensors like radar, LiDAR, multiple levels of cameras, and ultrasonic. WorldSim can be linked to a Simulink environment to couple with Car RealTime to bring a full traffic and sensor-rich offline simulation capability. The VI Grade Compact Simulator is an entry platform focused on subjective response for vehicle dynamics. It comes with a high-fidelity Cole-Morgan steering system that is capable of accurate steering torque and feel response, so you feel the design intent of the model you're driving and not the simulator. This is done with an included calibration process that allows for canceling out all hardware-related torque effects to provide a more model-true steering response. Similarly, we support active throttle and brake pedals capable of tuning to get design intent pedal feel. We include optional active belts to provide braking and deceleration cues directly fed from the simulation model. Similarly, the active seat contains multiple air bladders that an experienced driver uses to feel the lateral and yaw response of the model being driven. The solution uses a Barco projector with screen to provide a wide visual view. The Barco projector also functions as a replacement backup for DIM dynamic simulator customers that also use Barco projectors. Compact simulators are a great place to evaluate dynamic response when a larger dynamic simulator isn't needed or is not available, because it's built using the same computer and solver solutions that the larger VI Grade simulator use, Models can be tested and validated on a compact simulator prior to bringing to a DIM. This works as a way to reduce model check time on the dynamic simulator and also as a supplier test environment before sharing models with our OEM customers. In addition to the vehicle dynamics focused compact simulator, VI-Grade also provides a compact NVH simulator. In this version, the active belts and seat air bladders are replaced with shakers to represent 7 degrees of NVH vibration input, 8 if you include steering wheel nibble, which comes for free from the same Cole-Morgan steering system used on all VI-Grade compact and larger simulators. The NVH included vibrations are steering wheel vertical and lateral response, footwell or heel point vertical and lateral vibration, and independent seat vertical, lateral, and fore-aft vibration. The static simulator brings a more design intent cockpit. It also comes with a larger wrapped screen using multiple synced projectors for a rich and wide visual display. This is an excellent platform for multiple attribute solutions. It is a great place for doing ADAS or HMI evaluations. This solution comes with all the same modeling capability and typically includes the same steering and pedals that are available on compact simulators. If NVH response is desired, that can be included too using the exact same solutions that are available on a compact, but in a more immersive environment. This is an excellent solution for bringing in non-professional people for NVH jury assessments, for example. VI-Grade's flagship dynamic simulator platform is DIM, or Driver in Motion, which uses the same modeling solutions for vehicle dynamics, traffic, and sensors that we already covered. The DIM platform starts with a 6 degree of freedom hexapod solution of the DIM 50. This is an excellent solution for ADAS and HMI applications where onset of vibration response is critical. For example, transition from automated to driver control where the first cue of the driver is a dynamic braking or steering cue. It is also an excellent platform for evaluating ride events with dynamics all the way down to sub 1 Hz and up through 30 Hz and beyond. For those who want to include a broader vehicle dynamic response, there's also the DIM 150 and DIM 250 platforms. These provide 1.5 and 2.5 meters of dynamic travel, respectively, delivered on a 9 degree of freedom air-bearing solution that adds longitudinal, lateral, and yaw response with linear actuators. This, coupled with a world-class motion cueing solution, provides the best vehicle dynamic response. If even more dynamic response is needed, the cable-driven DIM 400 and larger simulators provides immense response. The platform provides a minimum of 60 degrees of yaw and 4 meters or more of traditional workspace, with designs that could support as much as 10 meters of travel. This allows, for example, a direct one-to-one lane change capability for slalom events, or greater than 90 degrees of yaw travel for true full turn ADAS events with dynamics. The DIM 400 is a cable-driven solution that's coupled with a hexa-lift solution rather than a hexapod. Part of that solution includes reaction masses that helps damp out response so that the system is as dynamically stable as possible. The other difference that comes with a cable-driven solution is the cables themselves are very quiet. So for combined vehicle dynamics and sound solutions, it's an excellent platform. And again, all of these solutions support the same modeling environments, including traffic and sensor simulation, as all VI-Grade simulators, on the absolute best dynamic response simulator for range and motion where it counts. But this talk is supposed to be focused on the desktop simulator. With the desktop simulator, you get all the exact same model capability that you get on the larger simulators. This includes full support for software in the loop and hardware in the loop solutions. When it comes to focusing on the simulation scenario and bringing the driver into the simulation response, this is as good as any simulator in the world. The focus here is on adding driver in the loop to the simulation environment without the larger investment needed to get the subjective feel of the response that compact and larger simulators bring to the table. The desktop extends offline simulation to include realistic inputs, and allows models to be checked with a true AI, that is the human driver, connected. The desktop simulator starts with a dual computing environment. First, we start with a concurrent real-time computing environment built on their Red Hawk real-time Linux operating system. Concurrent builds their solutions with hard real-time in mind. The solution comes with multiple cores for simultaneous simulation of different subsystem models. This might be a primary physics model with separate high-fidelity tire models, each being solved with their own core. It may include separate control models, either through SIL or HIL, operating on dedicated cores. Each core can be CPU shielded to guarantee real-time performance without operating system interrupts. The software solution is built on top of the concurrent simulation workbench real-time computing environment. This allows defining and tracking all interface degree of freedom between the various models in a simulation. On top of that is the VI DriveSim software solution that simplifies and defines all the communication needed to get the real-time solution to function across a multiple computer environment. This includes defining and managing multiple safety layers for a safe, effective driving environment. It includes a time machine capability for pausing, rewinding, and restarting solutions. It enables full open-loop playback for either previously driven events or real-time playing of slower than real-time solutions. This is the same simulation control center that the compact, static, and dim simulators use. In addition to the Red Hawk Linux real-time computing solution, the desktop simulator comes with a minimum of one Windows-based process that's used for graphics display. Graphics are provided with two VI-grade solutions. VI GraphSim has over 90 track environments available and is used by many VI-grade simulator customers around the world. And also, the desktop simulator comes with VI WorldSim, which is the same environment described earlier. In addition to the traffic and sensor simulation, WorldSim is built on the Unreal Engine. Sound is important on simulators. VI-grade simulators provide sound with specific channels based on separate sounds for engines and gears for internal combustion engine vehicles, motors for EVs, wind and tire noise. Standard models for GraphSim and WorldSim are provided. The VI SimSound software is included, which is the same solution used for more advanced custom NVH sound models, which can be added to the simulator as well. The desktop simulator comes HIL-enabled with a CAN bus card, and the simulation workbench solution enables integration of virtually any solution that can be captured and fed into a computer. Display is provided through two monitors, a large curved monitor for simulation graphics and a second console monitor for operating control. The driver interface is provided with included Fanatec steering, pedals, and shifters. These provide excellent state-of-the-art gaming quality interfaces, though they're not intended to fully represent model true torque and force feedback. For that, you need to move up to a compact simulator. Speaking of the model, desktop simulators come with a seat of VI car real-time. This includes all offline capability to allow model building, testing, and prep for simulator use. In addition to car real-time, VI Grade has a third-party solution testing program called VI Certified. With this program, we work with third-party providers to ensure that their solutions are tested and validated for use with VI-grade simulators. This includes physics plant models with solutions like CarSim, CarMaker, Adams Real-Time, Dymola, and SimPack. We also work with and test advanced tire models from all major tire model providers. Finally, we test and support use of some third-party graphics environments, in particular RF Pro. For simulation tracks and environments, a desktop simulator comes with a fairly large set of included and available solutions. We provide a 3-lane infinite highway for acceleration and deceleration and lane change dynamic testing. We include a VDA proving ground that comes with various size circles and a broad, wide area to drive on. It also supports adding cones for slalom and lane change tests. The VI WorldSim environment comes with over 40 residential, highway, and NCAP scenarios and test environments, and comes preloaded with the M-City test environment built in the Ann Arbor, Michigan area. Additional environments can be added from a library of over 90 scanned and rendered tracks worldwide. We also have the IDIATA Proving Ground scan with both handling and comfort roads for those interested in a commercially available proving grounds. And finally, we support building your own custom environments. This can be done through service support for scanning and rendering, or through a lower end approach by building road networks and graphics in the Roadrunner tool from MathWorks and importing into WorldSim. This could be done as service from VI-grade, or you could do that on your own. The desktop simulator I have described has the same content as our larger dynamic simulators. As with compact and static simulators, we also provide custom NVH solutions at the desktop level. This is a simulator that is designed to experience NVH sound and using an NVH virtual prototype model usable for any driving condition. This is a Windows-based solution that provides a real-time driver-in-the-loop experience in an environment with full control over the NVH data model and setup. If accurate vehicle dynamics is desired to allow proper acceleration and deceleration, including controllers, for example, or for capturing tire or steering system noise with precision, it's also possible to connect or merge the desktop NVH simulator with the Red Hux Linux vehicle dynamics solution previously described for a truly cross-attribute simulation experience on the desktop. There are a number of use cases for desktop simulators. First, as a platform for model preparation. This is for preparing models for use on larger simulators, for verifying real-time performance, and for setting up and checking sill and hill subsystem communication. It extends offline simulation to include driver-in-the-loop interaction, and it captures logged driver path and speed performance for feedback to offline simulation. As a sill and hill integration platform, it brings driver-in-the-loop to controller and other sill development, initial testing of ECUs and other hill implementations, and it lets you verify sill and hill subsystems before providing to other simulators. ADAS and NVH scenarios allow for test sensor layout and alignment with driver-in-the-loop. They verify ADAS scenarios and bring drivers with accurate vehicle dynamics to desktop NVH testing. One example of a customer using a VI-grade desktop simulation is FYCS. They are a chassis system supplier that uses a desktop simulator for chassis design at an early stage at the design process. This helps them meet their customer design requirements, tightening the connection between them as a chassis system supplier and the OEMs. We also have several customers using desktop simulators with hardware in the loop. In at least one case, local ECU controllers are integrated into the simulation model for evaluation. A more advanced application includes replacing the entire steering system with a custom hill setup. And one more example is Ford's use of a desktop NVH simulator. Chris Cundy from the Powertrain NVH group is one of our power users, and he presented at our 2020 conference. The presentation is available on our YouTube channel. Just search for VI-grade and you can find it. In that presentation, Chris reviews how the NVH simulator technology is used to make decisions faster and with more confidence when assessing Powertrain NVH design decisions. He presents several use cases, including one addressing electronic drive unit tonal noise. So in conclusion, a simulation-driven approach allows to increase innovation, front-load issues in the first part of the development cycle, and to decrease the development time, leading to safer products with less cost. VI-grade has a full lineup of simulators to address simulation challenges and needs from offline to full dynamic simulators, and a desktop simulator can play an important role making offline simulation and bringing driver-in-the-loop capability in an entry-level engineering platform that is consistent with and scalable to larger dynamic simulators. I hope you've enjoyed this presentation. Please feel free to request a demo of our technology at info@vi-grade.com. Thank you again for your attention.